All right, general chemistry. In this video, I'm going to walk you through the calculations involved in a titration problem and kind of talk you through how to organize your thoughts for those. So any titration experiment starts with a neutralization reaction. And acid-base neutralization is simply that, an acid reacting with a base to make it neutral. So we take a pH that would be low for an acid and pH that would be high for a base. We react them together and we get a pH in between. For a strong acid, strong base, that'll be pH of 7. So when mixed, an acid and a base react, and they neutralize. They will always react until one or both completely run out, which might be a strange statement for you here if you don't understand chemistry very well, but there are experimental reactions or chemical reactions where you can have both compounds available in the same container and they don't actually react because the temperature is not high enough or some other reason they're in the wrong phase or something else like that. Well, for an acid-base neutralization, anytime you get an acid next to a base, they're going to react. They can't hang out together. They're going to neutralize each other. And if you get the perfect amount of each, you get a neutral solution. So let's look at one example here. Hydrochloric acid and sodium hydroxide, if they get neutralized, the reaction would look like this. HCl is our acid, NaOH is our base, and they would react to produce H2O and a salt in HCl. And this would be table salt, but we're going to call a salt any ionic compound. That's our general term in chemistry for it. How does this work? How do we get our H2O? Well, the proton right here, acids donate protons. That's our definition. So it donates a proton over here. Our base has the hydroxide component. And when the proton and the hydroxide meet with each other, well, if you take H plus OH, you get H2O, and that's where our water comes from. So if I have the perfect amount of HCl and the perfect amount of sodium hydroxide, I can create a solution that doesn't have any more acid, any more base. It only has water and salt. And that's what a titration experiment does. We try to figure out exactly where that can occur. How much of each of these do we have to add to get a neutral solution? And some of you, if you chose the project with the red cabbage, you actually got to play around with that and try it out, neutralizing the solution. That's what we do with a titration. We just do it with an apparatus like I showed you guys in that earlier video that looks something like this. So let's take a look at a couple more neutralization reactions so you get the idea here, and then we'll look at the calculations involved in titrations. So what would it look like if phosphoric acid and lithium hydroxide neutralize each other? Well, my acid, phosphoric acid, is right here. My base is lithium hydroxide. And again, that would produce water and a salt, or a compound. Now, why do I need 3 lithium hydroxides? Well, you could just balance this in terms of atoms. But if you look at your acid and just stick to the definition of an acid, it's all of these guys. These 3 protons will all get donated. So how many hydroxides do I need if I'm going to neutralize all 3 of these protons? Well, the answer is 3 hydroxides. And that would require me to have 3 lithium hydroxide compounds. So it's a 3-to-1 ratio here. For the last slide, it's a 1-to-1 ratio. Let's look at another one, carbonic acid and barium hydroxide. You can pause the video and see if you could write that equation. It looks like this, H2CO3. And if you look at your chemical reaction here, I have 2 protons. How many hydroxides do I need? Well, the answer is 2, but there's already 2 for this compound. So this would be a 1-to-1 ratio. I have the perfect amount, 2 protons for this acid for every 2 hydroxides for the base. And if you got the perfect amount of carbonic acid and barium hydroxide, you would completely neutralize all the acid, all the base, and you just have H2O and barium carbonate left over. This should be a solid. I don't think that's soluble. Okay. So let's look at our acid-base stoichiometry. You're going to be using this to calculate your titration problems. So this is a good refresher, just to remind you how we do stoichiometry. How many milliliters, see if you can answer this question, of 0.5 molar HCl are required to neutralize 150 milliliters of 1.5 molar sodium hydroxide? The first thing you want to do is write your chemical reaction. So the reaction that occurs is this one. And we want to figure out how many moles are actually reacting. How do we do that? Well, we can't figure out the moles of HCl because we don't have a volume and a molarity. But we do have a volume right here, and we have a molarity of sodium hydroxide. And if you're given volume and molarity, you can calculate the number of moles of sodium hydroxide. If you don't remember how to do that, the capital M here actually means moles per liter. And so we have 1.5 moles of sodium hydroxide for every liter of solution. We don't quite have a liter of solution. We have something less than that. So I'd convert this into liters. This would be 0.150 liters. And I could convert from liters into moles. And then once I know the number of moles of sodium hydroxide that reacted, I can convert that to the moles of HCl that I needed. In this case, it's a 1-to-1 ratio. So if I had 2 moles of sodium hydroxide that needed to react, I would need 2 moles of HCl to completely neutralize it. And then I would take my moles of HCl and I'd convert it using the molarity of HCl. This is moles per liter. And I would get the volume of HCl required to completely react it. So let's look at that. This should be a refresher for you. Here's my known volume, my 150 milliliters. That's 1.5 liters of sodium hydroxide. Liters will cancel. I'm using my 1.5 moles per liter right here, my molarity. And then I'll get out of moles of sodium hydroxide using my 1-to-1 ratio from my balanced chemical equation into moles of HCl. Moles of sodium hydroxide will cancel. This will tell me the moles that I need of HCl to completely react all of the moles of sodium hydroxide. And then I'm going to get out of moles of HCl into liters. That's this ratio, 0.5 moles per liter. My concentration, I just flipped it over so the moles will cancel. And then I'll get into milliliters. And the answer is 450 milliliters. So what do I need? If you take a container and you have 450 milliliters of HCl at a 0.5 mole per liter concentration, and you dump that into a container that contains 150 milliliters of 1.5 molar sodium hydroxide, you will get a complete reaction, a perfect reaction. The HCl and the NaOH will completely react, and the only thing left in the container would be H2O and NaCl. Now, you wouldn't ever want to drink anything in a lab, but you could drink that solution, and you would be fine. It would have neutralized the acid and the base, and it'd just be salt water at that point. Let's look at one other stoichiometry one. How many milliliters of 15 molar, very concentrated, sulfuric acid are required to neutralize 575 milliliters of 2.5 molar lithium hydroxide? You can pause the video and see if you can calculate that. Here is your calculation. First, we want to use the correct balanced equation. Again, we have 2 protons here, so how many hydroxides do we need? The answer is 2, so we can produce our 2 H2O, so I need 2 of these for every one of these, and that's our stoichiometric ratio. Identify it. What in the problem can you calculate the moles of? Well, we need to be able to know the volume and the molarity for it. So in this case, it's right here. There's my volume, and there's my molarity. So I can calculate the number of moles of lithium hydroxide to start with, and then I can go from moles of lithium hydroxide to moles of H2SO4, and then I can go from moles of H2SO4 to volume using the molarity of H2SO4. So it'll look like this. Out of liters into moles for lithium hydroxide, out of moles of lithium hydroxide into moles of H2SO4 using your balanced chemical equation, a 2-to-1 ratio. And then out of moles into liters for HCl using the molarity. Again, capital M means moles per liter. So the 15 goes on bottom with the moles because I want moles to cancel. And then my 1 liter goes on top in this case. And then I'd get out of liters into milliliters. And the answer would be 47.9 milliliters. Again, just to repeat that, that's the perfect amount, the volume of H2SO4 required to react all of the lithium hydroxide in the 575 milliliters of lithium hydroxide. Now, that's the math behind it. For a titration problem, it's a little bit different because we don't know the concentration of one of these. So we'll be solving for the concentration. And the whole goal of the titration experiment using this apparatus is to figure out both volumes. So in this problem, we don't have one of the volumes and we solved for it. In our titration problems, we will know both volumes. We'll know this volume and this volume, and we want to solve for the molarity. But the concept here for the stoichiometry remains the same for all of these. So let's look at a titration. A titration has a setup, just like you saw in the previous video, and I described it. If you haven't seen that, you can go back and look at it. But in the burette, you'd put something called the titrant, which is just our solution with a known concentration. Let's just call that sodium hydroxide here. So we're dripping sodium hydroxide into an analyte, unknown concentration, and let's say that that's our HCl. We want to figure out what's the molarity of HCl, how many moles per liter for it. Well, we drip our sodium hydroxide in here until we reach the equivalence point. And the equivalence point is when the sodium hydroxide and the HCl completely react with each other, and we end up with a neutral solution down here. Oftentimes that's demonstrated by a little indicator, and the solution will change colors. Once I reach that point, I turn off the burette, and I measure between the initial reading and the final reading, and I'll get a volume. Maybe it's 25.7 milliliters of sodium hydroxide are required to react all of my HCl. Now, the basic understanding is this. If I know the volume of this, and I know the concentration of it, maybe it's a 1.5 molar solution, well, then I can use the volume and the molarity here to calculate the number of moles of sodium hydroxide that I added to this container. And that's how many moles of HCl I needed to completely react it to reach an equivalence point or an equilibrium point. And if I know the volume of HCl, then I can calculate the molarity. So let's look at that with some calculations here. So just an overview with words again. A burette is that device that we just add small amounts of solution, and you want to add small amounts until you have equal moles of H plus and OH minus in solution. You should think we're just neutralizing whatever's underneath. We're neutralizing the acid or the base. In this last one, we'd be neutralizing the acid of HCl. For a titration with a strong acid and a strong base, that neutralization occurs at a pH of 7. Remember, that's the only time that your hydroxide and your hydronium concentrations are equal to each other. And we call that the equivalence point. For an acid-base reaction, that happens when we just have H2O and NaCl left in our container if our chemical reactions between HCl and NaOH. So a curve would look like this. They would measure the pH of the solution. So they put a little pH probe in the bottom down here. And over time, that pH is going to increase because we have HCl down here. That's an acid. We start out with a low pH for the very start of the experiment. But as we drip sodium hydroxide, remember, these hydroxides come in and attach to these protons, and they make H2O. In other words, it starts to neutralize our acid down here. Well, as we get more neutral, that pH is going to get closer and closer to pH of 7. And we're not going to go into all the details for why it gives you a nice steep curve right here. It has to do with the equilibrium of water. But we're going to just talk about what it looks like on this graph. What point do we care about? We care about when it reaches that pH of 7, which is your equivalence point. And that'd be right here. And I go down from this point, and I'd go, oh, this is the volume of titrant I added. That'd be the difference between my initial and final readings. So that's what our experiment looks like. This value right here is the value that we're really looking for at the end of the titration experiment. Let's look at that in this problem here, and we're going to do calculation with it. So let's say that the titration began with 30 milliliters of HCl. So we have a known volume right here. We measured it. And the concentration of sodium hydroxide solution was 0.8 molar. So we have a known value here. It might be worth you just writing a diagram here. How many milliliters of sodium hydroxide were required to neutralize it? Well, I just go to my graph, find the pH of 7. I go down and I'd say, well, that's my 50. We had 50 milliliters required. So I would answer that 50 milliliters of 0.8 molar NaOH were required to completely react my 30 milliliters of HCl solution. Now, I don't know the concentration of this solution down here, but I do know that I needed to add this much base to completely react it. And that gives me enough information to solve for the concentration of the HCl solution. So let's look at that calculation. What is the concentration of the unknown HCl solution? Well, concentration is molarity, and molarity is moles per liter. And if I want to know the moles per liter for HCl, I need to know how many moles did I have in the container and how many liters of HCl did I have in my container. Well, if I go back to my page right here, we had 30 milliliters, so we know the volume. We just don't know the moles of HCl, but we can use stoichiometry to figure out the moles. So the volume is 30 milliliters. Convert that to liters. We're going to use stoichiometry to figure out the number of moles of HCl that had to have reacted, and we're going to do that by using the balanced chemical equation. So here's my equation. Hydrochloric acid and sodium hydroxide react. I know that I had to take 50 milliliters right here of my 0.8 molar sodium hydroxide solution. So my 50 milliliters goes here. My 0.8 molar gives me my moles per liter. And this would get me into moles. Liters would cancel, and it would tell me how many moles of sodium hydroxide did I need to react all my HCl. Well, it's a 1-to-1 ratio here. So whatever I get for my answer here, that's how many moles of HCl I had in my original solution. So I'm going to just do the stoichiometry there. It's a 1-to-1 ratio out of moles of sodium hydroxide into HCl. And the answer is 0.04 moles of HCl. So in this, I have 0.04 moles of NaOH. That's how much I added to neutralize my acid. Well, since it's a 1-to-1 ratio, that's also how many moles of HCl I had to have in my original container. And now I know enough information to calculate my molarity. Because I know my moles of HCl, and I know my liters of solution, it was measured at the start of the experiment, I can just plug those values in, 0.04 moles of HCl per 0.03 liters, and it'll give me my molarity. Now you can check your work here. The way to check if you did a titration experiment correctly, the math part of it, take this molarity that you got at the end, and the volume up here, 30 milliliters, and work backwards now using stoichiometry like we saw at the start of this lecture. I want to take this volume, go from moles of HCl, or milliliters of HCl into moles, and calculate how many milliliters of NaOH solution would you need to react all of my 30 milliliters of HCl. And the answer using this concentration will come out to 50. And if you get 50, you did it correctly. Let's look at another one. First, kind of a side note here. The first curve you looked at started out as an acid solution and went to a base because we dripped sodium hydroxide in. it's possible to start out with an unknown base. So at the bottom of my burette, I put a base down here instead of an acid, and I don't know what the base is, but I take my titrant, my burette, and the thing that I'm dripping into it here is an acid. And if that's the case, then we're going to start out with a low pH or a high pH, because we're a base, and that's where my pH is measured in that unknown solution. Then as I drip acid into it, it's going to decrease over time, and my equivalence point is going to be passed from the other direction. Still looks like a curve. I still care about the amount of HCl added, but you don't have to always have the thing underneath, the unknown being the acid. It could be the base. So let's look at one that is the base. This problem says 75 milliliters of barium hydroxide solution with an unknown concentration is titrated with 1.25 molar HCl. The equivalence point is reached when 13.5 milliliters of HCl is added. What is the concentration of barium hydroxide solution? Well, if I want to know the concentration of barium hydroxide solution, again, you want to think back to the molarity equation. I must know the moles of barium hydroxide, and I need to know the liters of barium hydroxide. Well, here's my volume of barium hydroxide, but the problem doesn't give me the moles. So I need to use stoichiometry for that. So a good way to start any titration problem, just read the problem and first recognize which compound did they give you a volume measurement and a molarity measurement. Well, in this case, it's HCl. There's my volume measurement, and there's my molarity measurement. That's the compound that you're going to want to start with. So for this particular reaction, we want to write out the chemical reaction for it. We're going to use that with stoichiometry to calculate our moles. So our molarity, the liters of solution that we want to figure out for our molarity of barium hydroxide is 75. This should say moles of barium hydroxide. That's what we're trying to calculate the unknown concentration for. And we're going to use stoichiometry to figure that out. Here's my balanced chemical equation. 2 HCl's are required for every barium hydroxide. Why? We only donate 1 proton here, but each one of these compounds has 2 hydroxides. So that's going to change my stoichiometric ratio here a little bit. And let's look at our math. We're going to take our known volume, our 13 milliliters of HCl, convert it to liters, and then using the molarity of it, that's how many moles per liter we have, we're going to get out of liters of HCl into moles. This will tell me how many moles of HCl I added in my titration experiment to react all my barium hydroxide. So then I want to use stoichiometry. That's my balanced equation, my 2-to-1 ratio, to get out of moles of HCl and into moles of barium hydroxide. This is how many moles of barium hydroxide had to be in my container with the unknown solution in order for it to completely react to the amount of HCl that I added. Then I can go back to my molarity equation here, and I now know enough information. I use stoichiometry to figure out my moles of barium hydroxide. I can plug it into my molarity equation. So molarity equals moles of barium hydroxide divided by my total liters of solution. And the liters of solution is just the liters that you started with for the known barium hydroxide right here. And if you plug those values in, this should say 0.075 liters of barium hydroxide solution. Then you would get this is your answer. Okay, I'm back. I didn't think I had my answer in there, but I do. This is your answer at the very bottom there, 0.113 moles of barium hydroxide per liter. Again, you could check your work here by taking your molarity of barium hydroxide, multiplying it by your volume, and getting the number of moles of barium hydroxide. Then use stoichiometry to figure out how many moles of HCl, work backwards, and figure out the volume of HCl required, and the answer should come out to 13.5. So this week you're going to be doing a couple calculations with that. Do that titration simulation. Do the titrations worksheet, which has a couple calculations just like we did in this presentation. And of course, if you have questions, you can always stop by the office hours or shoot me an email and I'll be glad to answer them. Hope you're doing well, and we'll talk to you later.